So we are doing chapter 21, activity 2, and this chapter is on carboxylic acids and their derivatives. And derivatives include acyl or acid halides, anhydrides, esters, and amides, and also nitriles, but they're typically not ranked in terms of reactivity. And carboxylic acids are not ranked either. So you're usually looking at amides, esters, anhydrides, and acid chlorides. And the acid chloride is the carbonyl carbon is the most electrophilic. It has the best leaving group, and in addition, the chlorine is inductively withdrawing electrons, making the positive charge more of a positive charge, and through resonance, it's not donating very well back to the positive charge. So it makes these carbons the most electrophilic out of any of the carboxylic acid derivatives. Between these two, this one is more sterically hindered, right? So it's not going to be, the rate will not be as fast because there'll be some hindrance towards the nucleophile coming in, because it comes in like at a 120-degree angle here. Kind of like on the front or the back side of that planar carbon. So I would say the most reactive is definitely D, followed by E. And then anhydrides are also pretty reactive, and they're sort of grouped as the most reactive with the acid halides, but not as reactive, not as good of a leaving group as a halogen. And I know the halogen is the better leaving group because it's the weaker base. So then C, being an anhydride, would be next, then esters, then amides. Hopefully, Dr. Wynn went through a detailed analysis of at least acid halides and amides to show you the difference in reactivity between the two. So in this case, the nitrogen zone pair is really donating heavily with the same sized p orbital, so very, very good pp overlap, and it's not a very good leaving group. So it's definitely the least electrophilic and the least reactive. Okay, and then generally the mechanisms are going to be what we call nucleophilic acyl substitution. So it's not exactly mechanisms, it's not going to be like an SN2, because you know you can't do an SN2 on an sp2 hybridized carbon, and it's also not an SN1. But it's still a type of nucleophilic substitution. We just call it an acyl substitution because the group here, instead of being an alkyl group, is an acyl group, and then this is the leaving group, right? So overall, it's a substitution, right, where the group is an acyl group. And it's a two-step mechanism minimum. So at the very minimum, we have to have at least a nucleophilic attack on the carbonyl carbon, and typically a resonance arrow here to avoid exceeding the octet. And then loss of a leaving group. And then there can be several more proton transfers as necessary to make good leaving groups, or to make this more reactive, which is sometimes needed, or to make this a neutral product in the end. So there could be proton transfers before this nucleophilic attack. That typically happens if one of these two is not strong, okay? So for example, if we have a strong electrophile, that overcomes a weak nucleophile in terms of having a reasonable activation energy and a reasonable rate. If you have a strong nucleophile, then you don't need a proton transfer because it's so strong that will overcome the activation energy as well. So at least one of these two needs to be considered strong, a strong electrophile or a strong nucleophile, for the reaction to proceed with the nucleophilic attack without a proton transfer, making this more electrophilic first. Okay, so good nucleophiles, that's like a Grignard reagent or lithium aluminum hydride, any of the hydride groups, or even hydroxide is considered a good nucleophile. So you guys probably know what are some of the good nucleophiles, right? So those are strong nucleophiles. Those generally don't need a proton transfer first. In addition, maybe this isn't strong, maybe it's water, the nucleophile, right? But it still might not need a proton transfer if this is a strong electrophile. So what are the strong electrophiles? They are the acid halides and the anhydrides. Those two are the strong electrophiles. So if you're starting from a strong electrophile, you don't need a proton transfer first, no matter what the nucleophile is. Could be strong, like hydroxide or Grignard, and it might be weak, even like water. Okay, and you still don't need a proton transfer because the electrophile's strong. So it's kind of like an activation energy barrier thing, right? We average out the energy of the electrophile and the nucleophile, and if it's super stable and low energy, then it's going to have a high activation energy. So like imagine, right, we're trying to get to this intermediate, which would be right here. And if the starting materials, the electrophile and the nucleophile are pretty stable and not reactive, they're not strong nucleophiles, they're not strong electrophiles, then they're pretty low energy, right? And that activation energy is going to be pretty high, leading to a very slow reaction. But if one of these two is stronger, that means that they are less stable. So it's like starting out higher, right? And then all of a sudden our activation energy gets smaller, right? So that's why we need either a strong electrophile, which would be an acid halide or an anhydride, or a strong nucleophile, for example, a Grignard reagent, hydrides, that sort of thing. Okay, so and we'll see a new one, I think, in this chapter as well. And even a hydroxide or an alkoxide, right, would be considered a strong nucleophile. So what if it's not a strong nucleophile, right, and it's not a strong electrophile? Like we may see cases where we use one of the weaker electrophiles and the nucleophile is not very strong, right? That's a problem. This is going to be too low in energy. So what can happen is you add an acid. What does the acid do, right? The acid is a catalyst and it protonates the oxygen, all of a sudden making it more electrophilic, right? This thing, once charged, is going to be higher in energy, and the carbonyl carbon is more electrophilic. So it's essentially making a better electrophile for the nucleophilic attack. So it proceeds at a good rate. So I think having a kind of understanding of when am I going to do certain proton transfers and when am I not, right? The first one, at least, it depends on the reactants, right? And if we don't have a strong nucleophile or a strong electrophile, we will do it, right? Later on, do we need to do a proton transfer before the loss of a leaving group? Well, it depends on if you have a good leaving group. If you have a good leaving group, you don't need to. If you don't, you do need to make a good leaving group, and then it will leave. So proton transfers may be necessary to generate a good leaving group. And then at the end, proton transfers may be necessary to make this neutral, right? If it's charged, like there's a proton attached to the oxygen, you would need to remove that. Okay, so let's just go through and look at a lot of examples, and I'll kind of reiterate what I've been talking about here as we sort of go through these examples. Okay. So here's sort of the ideas, right? At a minimum, we have to have the nucleophilic attack followed by the loss of a leaving group for these type of nucleophilic acyl substitution reactions. And then sometimes we will need proton transfers depending. And in the case of an acid halide or an anhydride, right, he points out, you don't need these two proton transfers because you already have a good electrophile, right? So you don't need the initial proton transfer to make a better electrophile. And you already have a good leaving group, so you don't need this one in the middle as well. So it tends to be a little bit shorter mechanism when you are dealing with an acid halide or an anhydride. Or in addition, it can also be shorter if your nucleophile is good. Okay, and we'll look at examples like that too. Okay, so here's an acid halide, right, which we know is the most electrophilic carbonyl carbon. And it's being reacted with water, which is a weak nucleophile. right? So even though this is a weak nucleophile, the fact that we have the best electrophile makes up for that. And we don't need any initial proton transfer. Cameron, mommy's on a Zoom meeting. I'll come out in a little bit. Go talk to your babysitter. Okay, so we're going to just do a direct nucleophilic attack without any initial proton transfers because this is already a good electrophile. So we're going to do a nucleophilic attack with the resonance arrow. Okay, so I think we're supposed to label it as a nucleophilic attack. Okay, and then we're going to do loss of a leaving group, right? And the leaving group is going to be the chloride. Is it possible to kick out the water? Yes, but that just goes back. So that's not very helpful, right? So to move forward with the reaction, we'll kick out the chloride, which is a great leaving group. This is a good leaving group, so we don't need to do any proton transfers to make it a good leaving group. Right? So we're just going to do loss of a leaving group. When we do that, we now have this, which does need a final proton transfer in order to be neutral. So we do need a proton transfer at the end here. So we'll just remove one of these. It doesn't matter which one you remove. Okay, so proton transfer. By the way, you might have been confused here when the next example has pyridine in it. And the point of the pyridine is actually to take the place of the chloride or the leaving group acting as a base. Okay, so I'll show you that when we do that mechanism. But basically, if the best base in solution is chloride, then we're going to generate HCl, which is a strong acid, which you might not want to generate in your reaction mixture if, for example, something in your molecule was acid sensitive. So this can be a way to avoid that. So essentially, as a base, we'll just use pyridine instead of chloride. And the byproduct will be what we call pyridinium chloride, which I'll show you. And I think he doesn't use it in the key, which is weird. Since he went ahead and put it there, he should use it in the mechanism. I think he accidentally used chloride in the mechanism. Okay, so we're going to draw a mechanism. So we're going to put in some lone pairs. And then we will remember that when you have an acid chloride, you don't need an initial proton transfer, so no acid is present. Okay, so we'll just do a direct nucleophilic attack. And then we'll get this intermediate here and put in the lone pairs for chlorine. And then remember that with chloride's a great leaving group because it's a weak base. So we can do loss of a leaving group, just like we did in the mechanism above. And then the only difference here, like I said, I'm going to use some pyridine. All right, so this stands for pyridine. And I'm going to use some pyridine to do the deprotonation. So pyridine looks like that. It's like an aromatic ring where one of the carbons is a nitrogen instead of, well, it's like benzene, but not exactly. Okay, so the lone pair is basic. And it's a better base than chloride. Remember, chloride is a very weak base, right? So we actually generated some chloride in this step. I forgot to draw it in. Okay. But pyridine is a much better base. And so it will likely do the final proton transfer here. And we'll get to this product, and the byproduct is pyridinium chloride. which is not as, since pyridine is more basic than chloride, the conjugate acid of that is a weaker acid. So this is not as strong of an acid as HCl, which can prevent some unwanted side reactions from happening. So when you need something to act as a base, you can add in some pyridine. Okay, so overall, what did we do here? We affected the transformation of an acid chloride to an ester, right? And all we had to do was add the alcohol, and it's optional to add in pyridine. So again, if you don't add in pyridine, you're going to get some HCl byproduct, which may or may not be a problem, right? So this is technically optional, and in some cases is advantageous to add to the reaction. But essentially, if you just mix an alcohol and an acid chloride, you will get an ester. And the reason that they'll react without really anything else catalyzing the reaction is because the acid chloride is so electrophilic. So we can get away with a weak nucleophile, which is just a regular old alcohol with no catalyst necessary. Okay, so kind of similar to the acid chloride is the anhydride, right? The anhydride has a good leaving group too, in that the leaving group is a carboxylate, so at least the negatively charged oxygen is resonance stabilized, right? So it has a good leaving group too, even if it's not as good as chloride, because it's not as weak a base as chloride is. It's still really quite good. So we will draw in some lone pairs. So because it's one of the more reactive of the carboxylic acid derivatives, we don't need any proton transfer to make this a better electrophile. It's already a good electrophile. Okay, and amine bases are actually pretty good nucleophiles. In fact, an amine is a better nucleophile than an alcohol, right? So the reaction will work even without any sort of catalyst being present. Okay, so we can do, and this possesses symmetry, a plane of symmetry. The anhydride has a plane of symmetry here. So it doesn't really matter which carbonyl you attack, right? So I just think it's easier because there's more room there to do that attack. So I'll draw it this one. Okay. And let's see what we formed here. Okay, so drawing out the product then after that nucleophilic attack, it looks like this. And remember that this is a good leaving group, right? So because the lone pair on this oxygen will be resonance stabilized, so that's why it's a good leaving group. So we don't need to do any proton transfers. We can just directly do loss of a leaving group. So this is when you break the ring open, right? So it starts to look a lot more like the product in this step. So we can kind of even draw it like the product, as much like the product as we can. Okay, so we have our carboxylate that we just kicked out here. And then I've got 1, 2, 3 methylenes. So 1, 2, 3. And then the next one is a carbonyl and the protonated nitrogen. Okay, so we did nucleophilic attack and loss of a leaving group there. And then to get to the product, all we need to do is a series of proton transfers. Basically, we need to lose the proton here and gain it over here. And I'm guessing there's more of this around than the protonated version, so probably deprotonate first and then protonate second. But it could be the opposite order as well. Okay, so I'm just going to draw in. So this is the base in solution, which is, by the way, also when you look at the skipping forward a little bit here. When you go to this here, little summary slide, right, of the reactions of acid chlorides, which, by the way, you could just substitute this with an anhydride. They do the same reactions. Okay, so the difference is the leaving group is different, but that doesn't really matter, right? It's like saying, should you classify an alkyl bromide different than an alkyl chloride? No, right? They just possess a different leaving group, but they react the same way. So anything that an acid chloride can do, an anhydride can do, and they pretty much the exact same way, just a different leaving group. Okay, it's just generally we don't really talk a lot about the anhydrides because they're not as common or easy to form as acid chlorides. So that's why we typically just use this. Okay, but the point was that I wanted to tell you, notice how when you're making an amide, which is what we just did, right, in this reaction, we were making an amide here, right? So it says excess of the amine, right? And you might have thought that was kind of weird, like why does it say excess of the amine? Well, the reason why is for exactly what we're doing right now, which is the second equivalent is used as like a base. So the first equivalent is used to do the nucleophilic attack that we already showed in the first step, right? And then we did loss of a leaving group and we got to this point. At this point, we need a base to do some proton transfer. So that's why we use the second equivalent. So it's excess just because one gets incorporated and the other amine is actually usually just used as a base. So instead of adding excess amine, you could add one equivalent of amine and one equivalent of pyridine, and the pyridine would act as the base. But it's just simpler. You're already weighing out the amine. You might as well just weigh out double the amount of that and have the amine act as the base, then add a separate amine, right, like pyridine. So it just depends on your exact application. If you would use pyridine here, or if you would just use two equivalents of this. Okay, so I'm just going to put two equivalents or excess, most likely is being used. Or you could use pyridine. And then pyridine would do the deprotonating here. Okay, so but if your amine is cheap, you would just use that. But if it's expensive, you would probably use pyridine, because you don't want to use your expensive amine as a base. Okay, so we're going to do our deprotonating. And then that will give us some protonated amine that we can use as an acid. To get to the product. Or some sort of acidic workup or something would probably be needed to protonate that at the end. Okay, any questions on this? Okay. So moving on here. The next part is to find the reagents and fill in the boxes. So to convert a carboxylic acid to an acyl halide, we need SOCl2. So that's one of the reactions you should just have committed to memory for this chapter. And there's a lot of reactions, right? So I did recommend at the end of last week, if you watched the office hours, to make flashcards, because there's a lot of reactions in this chapter. And then this is going to be our nucleophile, right? Substituting the chloride. So we will just add the nucleophile. Remember that we wouldn't write NH- because because we have no need of having a strong nucleophile because we have a strong electrophile. Like the acid halide is the most electrophilic of the carboxylic acid derivatives, and it will react with any nucleophile, weak or strong. So kind of adding a strong nucleophile is a little bit of overkill. You don't need it, so you might as well just use the simpler, weaker nucleophile and just the regular olamine. Okay, and then the selectivity demonstrated by the reagent. So you could have, the nucleophile could have been the alcohol or the amine, right? And so, and notice that the amine was the nucleophile. Not only is it better, more nucleophilic, but the product is more stable. Amides are more stable than esters. So we're forming the more stable product here, right? So we'll just say amines are more nucleophilic than alcohols, and amides are more stable than esters. Okay. So here we have some review reactions. So talking about in the past, we've learned that esters react with both Grignard reagents and LAH to have those strong nucleophiles do an attack, loss of a leaving group, and another attack, right? So we end up with either incorporating 2 hydrides or 2 of, for example, a Grignard reagent when using an ester, right? And then the key thing is that it incorporates twice because we have this alkoxy group, which can function as a leaving group. Okay. And then it's introducing here that acid chlorides really react the same way as esters in a lot of reactions because they also possess something that can act as a leaving group, right? And it's an even better leaving group. So should be even more reactive than the ester. So it will react with LAH, for example, to form the exact same product as an ester, right? The only difference is the leaving group is different. It will react with a Grignard reagent to form the exact same product as if it had been an ester. The leaving group is different, but otherwise they both react the same way. But there are some differences in reactivity with esters and acid halides. And that comes into play because we can utilize the enhanced reactivity of an acid chloride. Right? Do you guys remember when we talked about ketones and aldehydes and how the carbonyl carbon is electrophilic, right? And we said, you know, aldehydes are more electrophilic than ketones because it's a smaller hydrogen group here. But the acid halide is even more electrophilic than an aldehyde or ketone. So that's actually really useful, right? Because this is more reactive, more electrophilic than the aldehyde product. So we can take advantage of that reactivity, that enhanced reactivity, to find a reagent that will only react with the acid chloride and not the aldehyde, to be able to essentially stop at the aldehyde. Because look what happened when you used LAH. LAH is a strong enough hydride nucleophile that it attacked, we lost the chloride leaving group to form an aldehyde, and then it got attacked again because LAH is too strong. If you mitigate or decrease that reactivity of the hydride reducing agent, then you can have it only react with the more electrophilic acid chloride and not the aldehyde. So it won't react with aldehydes like LAH will. And the reactivity has to do with the fact that we have these bulky isopropoxy groups on the aluminum. And by the way, they're also electron donating. And so they just make it so that it's really, really going to react with this one only. Okay, looking over here, this is a new reagent. We haven't seen this one before. This is actually called the Gilman reagent. You can kind of think of it as similar to a Grignard reagent. Notice the use of the metal, right? In this case, it's copper, but in the case of a Grignard, it's magnesium. So what's the difference then, right? For example, between a methyl Grignard and a methyl cuprate. There's two methyls on the cuprate, right? So the difference is that we have not as polar a bond, right? If you look at the difference in electronegativity between carbon and magnesium, I forget what it is, but it's pretty high. It's like 1.5 or something like that. So there's a pretty decent difference in electronegativity here. It is much smaller for carbon and copper. For carbon and copper, the difference in electronegativity is like 0.6 or 0.7, I can't remember exactly what it is, but it's not as high. So what does that mean? That means that the polar, the dipole is not as strong. So this is a much stronger carbon anion than this one is, right? I'll draw that smaller, right? Because the difference in electronegativity is, and I hate to draw it in because I don't remember exactly what the number is, but it's, I'll fill it in later. It's much larger here than it is over here. So I'm just going to put large, large, small, I don't remember. And I don't feel like calculating it right now either. Okay, but anyway, the point is that the carbon anion on the Grignard is very nucleophilic. This carbon anion is not as nucleophilic. So how does that help, right? Well, when I use the Grignard reagent on an acid halide, it's such a strong nucleophile that it will attack the acid chloride. The chlorine would leave. I would get a ketone. And then it attacks the ketone, right? Because it's such a strong nucleophile. And we end up with this tertiary alcohol. But look at what the Gilman reagent does, right? It's a strong enough nucleophile that it will attack the acid chloride. The chloride would leave to generate a ketone, but it doesn't attack the ketone. Why does that work, right? Because the acid chloride is more electrophilic than the ketone is. Right? This is a stronger electrophile. So it will react with the weaker nucleophile of the Gilman reagent, but the ketone doesn't react with the Gilman reagent. So we're able to make a ketone, which is really helpful. Sometimes you want to make a ketone. You don't want to make an alcohol, right? You don't want to incorporate two methyls. You just want one. So it's advantageous to be able to go directly to the ketone. We can use the Gilman reagent for that. Okay, questions on this? Let's keep going and see some examples here. Okay, so we have an ester, right, with a Grignard reagent. So we know that the Grignard reagent is super strong nucleophile. It gets incorporated twice, right? So we can kind of draw the alcohol with two ethyl groups. Right, so we had to incorporate two ethyl groups. So this is really excess. It doesn't say it, but it is. And we've incorporated not one, but two ethyl groups. And for the LAH, it's going to incorporate two hydrides, right? So we can do, and you can draw in the bonds to the hydride here, to the hydrogens here, or not. Right? But it'll incorporate the two hydrides. So we also need excess here. Okay. Another Grignard, right, with an aldehyde. So these are kind of review reactions, right? Then we're going to incorporate two again, right? So excess, we're going to incorporate two of the Grignard attached to that carbonyl carbon. So we can do the alcohol and again two ethyl groups right? And then we have 1, 2, 3, 4, and then the OH group. So 1, 2, 3, 4, and then the OH group. Okay, and then the same thing here with the LAH. The only difference is what gets incorporated here is 2 hydrides instead of 2 ethyl groups, right? So we'll end up with basically a diol with 1, 2, 3, 4, 5 methylenes. 1, 2, 3, 4, 5. And then here now we have the Gilman reagent, right? So we know that it's only going to incorporate 1 ethyl, and we're going to make a ketone here at that carbonyl carbon. So it's going to be an ethyl ketone, and then the 4 methylenes, and then the alcohol. That was a leaving group. And then remember that this one provides the aldehydes. This is the bulky aluminum. Oh, you forgot the hydride in there. A little bit of an error. It's supposed to be aluminum hydride with 2 isopropoxy groups. Anyway, we're going to make an aldehyde here, right? So instead of a ketone, we're going to draw in an aldehyde. Okay, so these 2 are new reactions from esters that you want to learn. Make sure to include those examples of those reactions in your flashcards if you make them. So here is the summary, right, of the reactions of an acid chloride or an anhydride. Remember, we make them from carboxylic acids using thionyl chloride, SOCl2, and then a variety of functionality that we can make from that, right? So we can add in an alcohol to make an ester, and again, pyridine is optional here, right? We can add in ammonia to make a amide with an NH2 group. We could add in a primary amine to make an amide with 1 alkyl group attached to the nitrogen. Or we could even use a secondary amine, right, to make this doubly substituted amide. And then we can also reduce it just like an ester with LAH, and we'll get the alcohol. If we want to stop at the aldehyde stage, we would use that bulky aluminum reagent. Grignards will incorporate 2 of the R group, right, to make a tertiary alcohol. And then the Gilman reagent will allow you to convert directly to a ketone. So we want to make sure we know those reactions. And additionally, if you wanted to, you could, instead of using an alcohol, you could use water, and you would go back to a carboxylic acid. But that's how you made it, so doesn't seem likely that you would want to go back, but you could. Okay, some synthesis problems here. We need to introduce a carboxylic acid and then react that to introduce this aromatic group. So starting from an alkane, we always do radical halogenation first. And then from here, we can form a carboxylic acid where we add a carbon. We call that a 1-carbon homologation reaction. Because it's a tertiary carbon, you have to do the Grignard formation followed by addition of solid carbon dioxide, so dry ice. You're not allowed to do the sodium cyanide method. That will make the intermediate that we were looking for here. And then from here, we could potentially convert this to, so one way that's really common from a carboxylic acid is to make an acid chloride. And the reason for that is carboxylic acids don't have, they don't have a good leaving group. So they're not as reactive. right? But if you just use thionyl chloride and convert it to an acid chloride, now it is really reactive, right? And that can be advantageous. And then from here, we could just do a Friedel-Crafts acylation reaction with anisole. Right, so anisole and a Friedel-Crafts acylation. So this is a little bit weird because you're used to starting with the aromatic compound and thinking about adding the acid halide through the Friedel-Crafts reaction, but this is kind of like reverse of that. You start with the acid chloride and then potentially do the Friedel-Crafts where you add the aromatic compound. Because there's two organic things, so really either one could be your reagent and either one could be your starting material.
On the step with the Grignard reagent, do we need to protonate with water or hydronium?
Yeah, there would be an acidic workup. And so sometimes that's mentioned, right? They might mention H3O plus or water or, but yes, when you are making a carboxylic acid, you need an acidic workup to make sure that you isolate the protonated carboxylic acid. Okay. So over here now, it looks like we want to introduce the new carbon-carbon bond from that carbon, right? So we're going to do probably something you're pretty familiar with now, which is a 3-step sequence to get a bromine on that carbon, right? So first we're going to do our radical halogenation, followed by an elimination. I think we've done this many times, essentially, in different synthesis problems. And then an anti-Markovnikov addition of HBr, and that allows us to have the bromine at the less substituted position. Now we can do a Grignard reaction to form this new carbon-carbon bond. You have your choice here. You could do the same thing we did up here, right? Or you could, because this is primary, you can do the sodium cyanide method. So just to make it a little bit different, and again, this one, you could go either way with the reagent. So if you wanted to do the sodium cyanide method, you would use that, followed by a hydrolysis of the nitrile. So typically, you can do a basic or an acidic hydrolysis either way, okay? But acidic is more common. So, and then the good thing about doing the acidic hydrolysis is you're already using acidic conditions. So you will get the protonated carboxylic acid. You don't have to do an acidic workup separate. This gives us our substrate. Notice how we added a carbon, right, through that process. And then we just need to make an ester. So we can do SOCl2 to get to chloride, and then just use an alcohol. So this would be the propanol. And again, pyridine is optional here for the ester formation from the acid chloride. But okay?
I have a question.
Yes.
About that mechanism. In that really large reaction chart they give at the end of the video in the chapter, they have H plus ROH going from the carboxylic acid to an ester. Yep. Are we able to use that as the final step?
Yes. Yep. So that is another option you could do as well. So from the carboxylic acid, that's a good point. You can use what's called the Fischer esterification. So you can do a Fischer esterification, which involves the alcohol and an acid, strong acid catalyst.
Okay.
Yep.
Thank you.
Yep. Okay, good question. All right, next one. So we have starting from a carboxylic acid, it looks like we need to make a new carbon-carbon bond, right? We need to add these 3 carbons. And then we have an imine, so that probably was formed from a ketone, because that's how we know how to form imines. Right, so just sort of the last step is probably from the ketone, right? We're going to add the methylamine, so a primary amine, an acid to form the imine. So we're kind of really thinking about how do we go from the carboxylic acid here to the ketone where we've added some carbons. So there's probably multiple ways you could do this, but my first thought would be convert to a acid chloride. And from an acid chloride, we could use the Gilman reagent, right? So it's a little bit more complicated to draw the Gilman reagent, just because it's not, there's two of the alkyl group, and even though only one gets incorporated. And the way it's drawn is a little bit weird too. Okay, so I want to point this out. So this carbon is bonded to the copper. So it's kind of like, I guess, if you will, I'm going to kind of, you know, draw that out as the bonds to the copper. It's kind of ionic too. Right, so when you see something like this, this means 1, 2, 3 carbons, and this bond is like bonded to the copper, which is a little bit weird because it looks like 4 carbons, right? But it's just because of the way it's drawn. Okay, anyway, the Gilman reagent will produce the ketone, and then you can add in the primary amine. Okay. So we have carboxylic acid here, and we have an alkene. So I would say this one is very similar to the last one. Right? We're going to target having a carbonyl here, because we can make this through the Wittig reaction. Right, so we'll just do the ylide. So the steps to get from here to here are same as above. Okay. Okay, so fill in the empty boxes with structures. Okay, so here we have an anhydride. Remember that anhydrides react similarly to acid chlorides, right? 1/2 of this essentially is just going to be the leaving group. So we're introducing the acyl group onto this and onto the alcohol here, because this is an alcohol. So we have to draw out the S2 pentanol so that we can get the stereochemistry right here, right? So 2-pentanol, and then if we want it to be S, for example, let's see if we had the OH down, let's see if it would be S. So 1 to 2 to 3 with the hydrogen coming out at you, right? So this is clockwise, but the hydrogen's coming out at you, so this is really S. So we just want to make sure that that stereochemistry is preserved here. We'll add in that acyl group. So basically this reaction is just a reaction between an alcohol and an anhydride, which is similar to an acid chloride, to make an ester. Okay, here's another reaction of an anhydride. Just remember that, again, this is the leaving group, right? So it doesn't show up in the product. So we need to use a nucleophile, and then we just need to remember that amines are actually strong nucleophiles. Okay, so typically you would use an excess for one equivalent to act as a base there, or an equivalent of purity. Okay, So these are the conditions to form an epoxide, right? If you recall, it doesn't say show stereochemistry, so I guess we won't bother. And in contrast to this one, which is very clearly show stereochemistry. We just need to make an epoxide for that one. So that's a review reaction. So this, you might recognize this from the last chapter, right? So everybody can see that. This is a hemiacetal, or a half acetal. Right? And so that is formed from an alcohol and a ketone. Right? So this will have been where the carbonyl was, and this will have been the bond formed with the alcohol. So if we draw the starting material over here, we've got the ketone, right, and then the 1, 2, 3, and then the OH group. So 1, 2, 3, OH group. This one is a Wittig reaction, so we need to draw in the ylid. Okay, this is a reaction of an acid chloride with hydroxide. So this is one of those reactions I would call overkill, right? Because you could just replace this with water and it would do the same thing. With hydroxide, now we have a strong electrophile in the acid chloride and a strong nucleophile in hydroxide. So this is going to be a very exothermic reaction. It's going to get hot really quick. You'd have to cool it in ice and be careful and add it drop-wise sort of thing. Otherwise, it could potentially bubble over or, you know, make a giant hazardous mess. Because this is going to, think about the activation energy here for these two. These are both super high energy, super reactive. So we're talking about high energy. It's going to have a teeny little activation energy and it's going to go boom like that. So you have to be careful. So actually, this is a little bit of a weird thing to do. You could just use water to get the carboxylic acid. But if you did this, you'd have to just be really, really careful. And you would get the carboxylic acid though, because it would do a acyl substitution of the chlorine. It doesn't say acidic workup, but I'm assuming an acidic workup, right? Because in the presence of base, actually this would be deprotonated. The carboxylic acid would be deprotonated. So immediately the sodium hydroxide would deprotonate the carboxylic acid. So you would need an acidic workup, right? So we're kind of, I'll just write that we're assuming an acidic workup. That's why we've drawn the protonated carboxylic acid. Okay, so these are conditions to generate a tert-butyl cation, which will do like a Friedel-Crafts alkylation reaction to introduce the tert-butyl group, which is a ortho-para director. So it will direct the next group para to it. NBS and heat is a halogenation of benzylic positions that have a hydrogen. So we'll put a bromine there. That sets us up to be able to do this carboxylic acid forming reaction via Grignard with dry ice. Make sure you're adding a carbon when you draw the product. Right? Some people might accidentally draw the carboxylic acid on the benzylic carbon. But make sure that you've got that extra carbon in there. And then thionyl chloride will convert this to an acid chloride, which will react with a secondary amine to make an amide. So 2 methyl groups.